Alright, let's talk about more equations. Specifically, we're going to talk about equations that deal with work, energy, and power. So work, we remember the formula force times displacement. And force times displacement works if we have a constant force and it's in the same direction as the displacement. If that's not the case, work equals the component of the force that is in the same direction as the displacement multiplied by the displacement. So we could say F d cosine theta. Or in other words, work equals the dot product of the vectors, force dot displacement. So this will get us the work if we have a constant force. If we have a non-constant force, we have to go with work equals the area under the F versus X graph. Now, I say F versus X, but it could be an F versus R, or whatever linear variable you want to use. So area under a force versus position graph, basically, is what we're talking about. And so area, we know, is a fancy non-calculus word for the calculus word integral. So work done is equal to the integral of force dx, or FDR. Again, xr, doesn't matter which variable you use there. But the integral of f dx, that's the work. We also have potential energy. That's defined as minus the work done to get from a reference position R to a position P. And because work is equal to the integral of f dx, then potential energy function is equal to minus the integral of f dx to get from position R to position P. Position R is defined as the reference position, the position at which the potential energy function is equal to 0. And that will give us then our potential energy at position P. Now, the flip side of this equation, if I were to solve this for the force is equal to minus the derivative of the potential energy, minus du dx, or minus du dr, again, depending on the variable you're choosing. So again, integral means area, derivative means slope. So if I'm given a problem where I've got a potential energy function that's graphed, and it asks me where is the force equal to 0, I simply find where the slope is 0. Or it could ask me where the acceleration is 0. And I know that force equals mass times acceleration. So where the force is 0, the acceleration would be 0. So I could find the slope there. So these relationships do come in handy. We also have, for energy, kinetic energy is 1/2 mv squared. And then we have some potential energy functions that we've defined. Potential energy gravitationally in a constant gravitational field is equal to mgh, or mg delta h if you wish. It's really just h here is referring to the displacement vertically, the change in height, like that. We also have spring potential energy is 1/2 kx squared. X again being a displacement, it's a delta x really, it's a change in the position of the spring. And then we also have, for gravitational in the universal sense, universal gravitation, where we're looking at the force is equal to g mass 1 mass 2 over r squared, for example, then the integral of that, if we work that out, we would come up with this formula, minus g m1 m2 over r. So that is our potential energy gravitationally if we're talking about a non-constant gravitational field where we're looking at a universal gravitational situation. So those are some of the basic equations of work and energy. We have conservation of energy. Conservation of energy implies that in a given scenario there's an initial and a final condition, that the initial energy of the system is equal to the final energy of the system. Now, energy can be transferred by means of either work, radiation, or heating. In physics C mechanics, we're basically just talking about work as a mechanism of energy transfer. So we could technically write this as energy initial plus the work that's done is equal to the final energy. And as we can see from this equation, if I solve it for work, I get work equals E final minus E initial, or in other words, the change in energy. That's the work that's done. Often we look at the work kinetic energy principle where the potential energy is not changing, and we simply say work equals delta K, the change in kinetic energy, is equal to the work that's being done. Power is defined as the rate at which work is done. So by that definition, we come up with the formula. Rate simply means something over an amount of time. So the work that's done over time, or since work is equal to the change in energy, power is the change in energy over time. Or there's another formula we can get at, which is power equals force times velocity. Now, this change in energy over time sometimes can be written as a time derivative of energy. So dE dt, the rate of change of time, or dW dt, you know, any rate can be written as a time derivative, for example. So those are some basic equations for power. Now let's talk about center of mass. Center of mass equation basically says that if I have a collection of particles, I can find the center of mass by the position of the center of mass would be the sum of mx's divided by the sum of the masses. Now what that really means is I'm going to take each mass times its position, so m1x1 plus m2x2 plus however many I have, and I'm going to divide it by m1 plus m2 plus however many I have. So you take each mass, multiply by its position, add them all up, and then divide by the total mass. That will give you the position of the center of mass. I can do the same thing for the y position of the center of mass. I can do the same thing for the velocity of the center of mass. I would use m times v. Or I can do the same thing for the acceleration center of mass. So that would be m times a, m1a1 plus m2a2, and so on, divided by the total mass would give me the acceleration center of mass. So that's our basic center of mass formula. Now let's talk about momentum. Momentum is the quantity of mass times velocity. The symbol we use for momentum is p, so the basic equation p equals mv. Or as we learned, mv equals p, mvp. So p equals mv, that's just momentum. Impulse is a fancy word for the change in momentum. So the change in momentum is the impulse. Symbol we use there is a j, so j equals delta p. That's the change in momentum. Now, we could also find the change in momentum by taking mass times change in velocity. Delta, remember, is final minus initial. And I can also find momentum by taking force times time, or in the calculus sense, integral f dt, which is a fancy way of saying area under a force time graph. Let's try that. There we go. So those are all ways of finding the impulse. So the nice thing about this, having lots of ways to find it, is in a given problem that's dealing with impulse, I can pick any two of these and set them equal. For example, if I have a graph, I can shade in and find the area. And I know that the area is the impulse, and the impulse is equal to the mass times the change in velocity. So if I know the mass, I can figure out the delta v, or if I know the delta v, I can figure out the mass. It works out really well. So those are some basic momentum equations. I also have the equation. We know how the net force equals mass times acceleration. Well, the net force actually is equal to dp dt, which is the rate of change of momentum, how much the momentum changes in time. And this equation, the net force equals dp dt, this is what tells us about momentum conservation. Because if the net force is 0, then the rate of change of momentum is 0, and that means that the initial momentum has to be the same as the final momentum. So if the net force is 0, then momentum is conserved. And conservation of momentum says that P initial of a system is equal to P final of a system. Or in other words, M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. Or, you know, various iterations of that basic equation. It's you look at the system before and add up all the MVs, look at the system after, add up all the MVs, and they will be equal where the net force is 0. That's what we mean by conservation of momentum. This will bring us to the idea of elastic collisions. Now, most collisions are not elastic. And in fact, there's a special case called a sticky collision, which is definitely not elastic. It's all sometimes referred to as a perfectly inelastic collision. If two things collide and stick together, not elastic. But if they collide and bounce, there's a chance that they could be elastic. The elastic collision is defined as a collision where both momentum and kinetic energy are conserved. Now, in most collisions, kinetic energy is not conserved, which is not to say energy is not conserved, it's just kinetic energy is not conserved. Because sometimes in the collision, some of that original kinetic energy is dissipated as heat, it causes changes in the shape of the object, sound, lots of different places where that kinetic energy can become dissipated or turned into other forms of energy. But if we have a case where kinetic energy and momentum are conserved, then I can use both conservation of momentum equations and conservation of kinetic energy equations. And we'll notice from conservation of momentum, m1v1 plus m2v2 equals m1v1 final plus m2v2 final, right? And for kinetic energy, 1/2 m1v1 squared plus 1/2 m2v2 squared equals 1/2 m1v1 final squared plus 1/2 m2v2 final squared. Now, as you can see, the kinetic energy equation and the momentum equation have the same variables. Now, in class, we derived an equation that we called the Koch equation. Koch stands for conservation of kinetic energy. And we found it easier to use than this one, because in this one the v's are squared, and you end up dealing with quadratics. Not that it's hard, but it does take more time. And on a timed test, efficiency is very important. So our Koch equation that we derived, conservation of kinetic energy, it says that V1 plus V1 final equals V2 plus V2 final. So anytime I have a collision that I know is elastic, I'm going to go with conservation of momentum and my Koch, my conservation of kinetic energy equation. That gives me two equations, which allows me to have two unknowns that I can then solve for.